Okay, dear colleagues, let us start our BIM's Integrable Systems seminar, and today our speaker is Oleg Chalykh about integrability of Inozemtsev spin chain.
Okay, thanks very much. It's a pleasure to give a talk here. So I will talk about Inozemtsev spin chain. So this is so-called long-range spin chain described by this Hamiltonian, written here. So it was introduced by Inozemtsev in 1990. And so here you have P function with periods 1 and tau. And Weierstrass P function, so elliptic P function. So you think of this as acting on the space U, which is a product of copies of some, say, finite dimensional space CM. And so you know, in physics language, you think of this as n sites, and this space is your spin state at this site. And so elements Pij act by permuting the factors of the tensor product. Pij permute the factor. So there is action of symmetric group on this by permutations. Okay. And so so this is called a long-range spin chain because interaction between spins here appears, you know, not only neighbors interact, but this coefficient which indicates the strength of interaction. So it's non-zero for all pairs of I and J. And so a problem, typical problem, one of the questions, so in general, the question is whether this is integrable, but one aspect which I will be talking about is whether you can find so-called conserved charges for this Hamiltonian. So you would like to find elements of endomorphisms of this space, so just linear operators acting here, which would commute with H. Not known. Not known. And so Inozemtsev himself, in his first paper, he found two commuting charges, which I wrote here. So here I'm using notation. So elliptic zeta, this is P prime. And then, for example, if I have something like that, it means that I evaluate similar to the formula in the Hamiltonian. I evaluated this I minus J over N. So, right. So you could think of this term as indicated that your sites are equidistant on the circle because one is a period of P functions. So you can then think of this as a distance. So your period 1 you divide by with the step 1 over n. So this is a distance between I and J sites, and that's the interaction, the strength of interaction. Okay. So so it's an interesting problem. Yes. So he came up with this. In his papers, it says, well, just by just using kind of just guesswork, and then he proved in that paper that both commutes with H, although maybe some calculations were too long to include in the paper, and then for example, commutativity of I1 and I2, he proved with Dietrich some 15 years later or something like that. And commutativity of that fact that yeah. So this was done. He couldn't do maybe in his initially at that time, and this was done much later, and it's like several pages, like 8 pages of calculation with elliptic identities, right? So it's a curious case of something which is expected to be integrable, but no kind of method for producing this was known, and maybe, I don't know. I don't know. Yeah, well, checking commutativity probably, yes, can be done on a computer now these days. Yes, if you give formulas. Yes. Yeah, so certainly, well, in this calculation, for example, they say that, well, we prove this, but for that we need some new elliptic identities, So it's not so simple, and so even with a computer, maybe difficult. Who knows?
When it's pi over something greater than 2 or 3, it stops computing.
I see. Yes. Yes, trigonometric version of that is well known as Haldane-Shastri. Yes. Yes. And so there you have all this beautiful story and 1 over sine squared. So when you have beautiful story with Yangians and everything, and it is well known as integrable spin chain, and so this one was widely expected to be integrable, but from this calculation, Inozemtsev in one of the papers, I think around 2003, he introduced some infinite sequence of these i's by some sort of complicated recursive formula. And as far as I understand, he proved that they all commute with h, but could not do something about their commutativity. So this was a well-known problem, and maybe not many people tried, because at least that was my thinking. If Inozemtsev wasn't able to do that, then probably he's a master of elliptic functions and identities. So right, okay, but ideally you would like not just to produce maybe some formula, but to have maybe conceptual explanation for that. So that's what I'm going to explain. Right, okay. So not surprisingly, the mechanism behind the method is related to, well, it is known conceptually that this somehow should be related to so-called freezing trick applied to elliptic Chalykh-Moser problem. And so certainly elliptic Chalykh-Moser problem should tell you something about this. And as we know now, the best explanation of integrability of elliptic Chalykh-Moser problem, well, one of the good explanation uses elliptic Dunkl operators. So that's what helps here as well. So what I will explain how you can construct conserved charges from Dunkl elliptic operators, elliptic Dunkl operators. Okay, so let me now, this was introduction, so let me move on to explaining this a little bit. So the ingredients we need, so elliptic Chalykh-Moser system and Dunkl operators. Okay, so we have classical and quantum. And so classical system looks like this, and And then it has a quantum analog, and both are integrable. Okay, so p hat is the quantum momentum. And at the classical level, there are n boson commuting Hamiltonians. And at the quantum level, there are commuting quantum Hamiltonians. And they can be constructed, both can be constructed quantum and classical using quantum and classical Dunkl operators. So just to, later on, I will be speaking about this. So these are all functions of p and x. X and p, I will be writing. So x1 to xn and p1 to pn, momenta. Okay, so that's symmetric function of 2n variables. So I will be writing it like, sometimes you will, if you will see something like that, I mean just function of x and p, which is invariant at the simultaneous permutation of x's and p's. All right, okay, so that just, and then Dunkl operators, yi is pi, if it's a quantum version, and then plus g. J different from I, and what do I have? Phi. So let's use phi. That's this Kronecker function, which often appears in the elliptic integrable systems. Okay, so that's so these were introduced by Buchstaber, Felder, and Vesilov in 1994. Yes. And the main properties, yes, so maybe I should say, I should write this phi of z mu is theta of z minus mu normalized like that. So theta is odd Jacobi theta. Okay, so that's so these are elliptic Dunkl operators, and they commute. The main properties are commutativity. Thank you. Yes, yes, a good question. So these y's, maybe I should, before stating properties. So these y's, maybe I will use the linear combination. If I pick any vector psi, I can take a sum of these xi I yi. So this is an element. So I view this as so there are clearly differential operators. So on the space V, by V I will mean just x variables, and crossed with the symmetric group. So this algebra is generated by differential operators, so functions, derivatives, partial derivatives, and everything you can build out of that, and group elements. And group elements, if you move them around, they act on x and derivatives, right? So this is an element of this algebra. No, not on lambdas. Yeah, that's important. Yes, thank you. not on lambda. So lambda just auxiliary, yes. So I would say lambda dependent elements, right? So you can introduce extra space where lambda lives, but I will not do it in this notation. So just you think of them as family, depending on lambda. So lambda here are additional variables. Sometimes they're called dynamical, but I think it's unfortunate name. So I will call them spectral variables. So you have n of those. Okay, so the main properties of is commutativity, and then equivariance. Equivariance, so W, any element of the group lives in your that cross product, that algebra. So if you do something like that, maybe I will stress that it depends on lambda. And then you get a Dunkl operator with corresponding to new direction. You act by W on psi, and simultaneously you need to act on lambda. Okay, so yes, so they commute as just as given, yes, with fixed lambda, yes, and all right. So now the idea. Usually, when you see Dunkl operators, the idea to construct this integrable Hamiltonians is to take symmetric combination of Dunkl operators, maybe restrict on symmetric function. And here is a problem: if you take symmetric combination of y's and start acting by W, because it acts on lambda, it is not. It is not W invariant. Just W invariant combination of y's will not be W invariant, right? So, for example, the sum of squares. Okay, so let's see. So you would like to get rid of this lambda, and the idea is everything would work fine if for lambda you choose a fixed point for the action of the group, then everything would be fine. It will be just, but the only fixed point here would be the origin. So you need to take lambda to 0. And if you look at the formula for Dunkl operators, they have singularities when lambda approaches 0. So that's the solution to that is so construction of elliptic allogomorphic Hamiltonians was found by Ettinghoff, Felder, Ma, and Vesilov. And so it's best summarized maybe in steps. So first you take symmetric combination of y's, regularize. So take it with some lambda dependent coefficients. So regularize. So it is regular. It has limit when lambda approaches 0. So you take this limit, you will obtain a symmetric element in this cross product, and then you apply and this limit lives in this algebra, so it still has group elements here which you need to get rid of. So that's the standard procedure. So I say erase all the group elements. So this usually is done applying the restriction map. So if you have something which has group elements appearing there, you just erase them. That means you just take the sum of these. So these guys, they are in differential operators. Okay, so you get something which will be just purely differential operator. And so if you do that for all possible symmetric combination, for example, elementary symmetric function of y's, then this will produce a complete set of differential operators, which will commute automatically because they were produced from commuting quantities y's. And yeah, so the main work is to explain how do you regularize. So which expressions actually work. So if you take just, for example, if you start with the sum of squares of the, so it's a good, maybe it's a good example. If you calculate the sum of squares, then well, okay, I will not do a calculation in here. Just write down the answer. So what you get the sum of squares of momenta, and then you get something like the sum of the function of, I will use the shorthand notation for pairwise differences. And then there is something like minus 2g h bar, sum I less of than j phi prime, derivative of that Kronecker function of lambda ij, xij, sij. Okay, so well, the first variable, say, for it's symmetric, so it doesn't matter much. But let's say that phi prime means my definition for phi was variables z and mu. So let's say with z. Okay, and so that's the singular terms, right? Second order poles here, so they blow up as lambda approaches 0. So you would like to remove them. So the combination to take, so regularization, you take the sum of y squared as was before, and then subtract 2g squared so this removes the singular terms, because this function actually, phi was singular at lambda equals 0, but when you take regular at lambda equals 0. So when it approaches this, tends to, actually when z goes to 0, or lambda goes to 0, in this case, when mu goes to 0, it's the, yeah, I think I was switching from between the, okay, so in my lambda goes first x, then probably, okay, it doesn't matter. So, okay, so maybe for consistency, it's better to use mu here. And when mu goes to 0, it tends to minus the function of z. Yes, so this is regular at when this approaches 0, and so if you do this limit, you get indeed just the sum of p hat. You get this. Okay, let me record what you get. I'll write it in a slightly -2 sum over Pxij, and here we'll write G times G minus H bar Sij. So at the moment, I'm still keeping these group elements here. And then if you apply a restriction map, Sij becomes identity, and you get the quantum Hamiltonian. Okay. So the clever kind of idea these people had was that the process of regularization actually can be explained in the following. You just need to substitute. This looks more or less like a classical Hamiltonian, you see, if you look at H. So that's what works in general. You take classical Hamiltonian for the, okay, well, it's not what they did in their paper, but let me maybe formulate their recipe. Substitute y's and lambda into classical rational. What works actually, if you look at the rational Hamiltonians as function of x and p, you don't need more complicated elliptic ones. It still works. Sorry? So y's, which you substitute, they will have lambda. So you replace x with lambda. So what you do, you just, because y's are commuting operators, you can substitute them as instead of variables, instead of momenta. So replace momenta with elliptic Dunkl quantum elliptic operators, and instead of classical momenta p, and x replace with lambdas, and then and this you can. Sorry. Well, the average with the one group is taken care of this Hamiltonian because it's already symmetric. So the leading term in this, in terms of momenta, will be symmetric polynomial in Dunkl operators. And these extra terms which appear in the Hamiltonian, that's they do regularization. So example which Yeah. So instead of here, what they did, they use 1 over lambda I minus lambda j squared, which would also work because it will be just different by a constant, but it doesn't matter. Okay, all right. Yeah, no. Yeah, literally the same. Yeah, in this case, yeah, yes, you're right. Thank you. Yes, but if you go to, yeah, okay. So that's the recipe. Okay, and so if you go to here, you get something which I yeah. So applying limit lambda goes to 0, and then applying this restriction map produces this H elliptic quantum Hamiltonians. Okay, right. So now we need to get closer to Inozemtsev spin chain. You need also spins. So this is just a elliptical Roger-Moser system without spins. So we need to introduce a spin version of that. So that's spin elliptic Chalykh system. Okay, so here we need to, I just write the it's this idea is well known since 90s or 80s, I don't know. So what I'm doing now is kind of known, but not quite. So we need some extra extra supply. So what will happen? Yes, I'm going to write Hamiltonian where this is replaced by Pij. Yeah, Pij. Yes, so that's the. I will put spin, and that's just this thing, which appeared already. Minus 2 the function of xi minus xj, and here you have g minus Pij. Okay, so this operator you think of similar to Inozemtsev one, so you have also dynamical variables. So it's differential operators, and then tensor product with an homomorphism of our space U. So again, Pij act by permuting tensor factors, but now they don't interact with axes, right? So this is now just the tensor product. So that's the Hamiltonian of the spin quantum spin Chalykh system, and the way we get it was just we replaced Sij by Pij. So in general, there is a method which can work more generally. So that's the. So for that we need maybe a spin version of this restriction map. So if you have something which was, like coming from Dunkl operators, so it was in this cross product, you want to get out of it a matrix differential operators. So that's here. And the way you do it, you just send any differential operator times, if you have anything like that, where you put all the group elements to the right, push them to the right, then this becomes just the sum. I will use notation like that. The P representing W inverse. Okay, so that's the map which you need. Okay, it converts elements here to matrix differential operators, and it's not an algebra homomorphism. So commutativity, if you have anything which commutes here, it does not necessarily commute in the image, but what works, so this becomes an algebra map when restricted. Okay, maybe I should, okay, maybe I, instead of, okay, when restricted. So you need to choose elements which are Sn invariant. So symmetric elements here. So here Sn, there is a conjugation, natural conjugation by W. Here it works in the cross product. So if you restrict on this, on such guys, then this is algebra homomorphism. And so if you find, now you need to find commuting elements here. If you find commuting elements here, many of those, sufficiently many of those, you would produce commuting matrix operators, which we can view as kind of, yeah, higher Hamiltonians commuting with this. All right, so now the question is how to find this combination that works. And what was kind of understood, then of course you can take the same combination as in this Ettinger-Felder-Mar-Vesilov. So you can take just a regularized symmetric combination of y's, right, and apply that. So doing this, yeah. So the question: which combinations again of y's and lambda? Already we saw in the previous construction that you need not just combination of y's, but you need to lambda. So, okay, maybe just which functions. You think of function of x and p, symmetric, and then you substitute lead to, you do the same. You substitute with lambdas and y's that are regular. Okay. So what the calculation we've done, we had just sum of squares regularized, and then it makes sense to take lambda equals 0 limit, and then using not the restriction map as before, but the spin restriction produces spin Hamiltonian like this, and the same method works with these guys as well. But so that would produce, if you just use those, you produce n commuting Hamiltonians and commuting spin Hamiltonians. But that's not enough. You would like to have more, because spin model has more degrees of freedom, so you would like more of them. So the answer, so F should be in what I call BG. It's spherical rational spherical Chalykh subalgebra. So it's a deformation. It has parameter deformation G, the coupling. If G is 0, it is just if your Dunkl operators had with G 0, it will be just partial derivatives. You take just symmetric combination and nothing else. But here it's deformation of the so-called double invariants. So polynomials which are invariant, polynomials of two n variables, invariant and the diagonal action of the symmetric group. And so this has an interesting deformation, actually Poisson deformation. That's a Poisson algebra. And it can be described I can describe the set of generators, but maybe I'll skip. Okay, maybe let's see. Yes, so maybe I will give a proposition. So if you, so this one, by the way, by the result which is usually attributed to Weil, although it was known long before, So this B0 is generated by, you take traces of, okay, maybe sums x I to A, y I to B, sum over y I to n, and I'll call this function f. AB. And deformation, the spherical subalgebra is generated by, okay, this can be seen as a trace of the product of two diagonal matrices in powers A and B, and so that's what appears here. It's a trace of, I will write it like that, where x is diagonal. Okay, here I'm using, yeah. And Y is a matrix which has, I need P and X, right? P variables appear on the diagonal. And G divided by Xi minus Xj, if I is different from J. That's just well-known Lux matrix for a rational Chalykh model system. And so the recipe to get deformation, or some deformation actually, is just to look at the traces of these products. So you take powers. If A is 0, for example, you get powers of Y. These are just rational Hamiltonians of the which appeared in the construction before. But you're also allowed to put some powers of X, and so that so this produces more than just n Hamiltonians. So the extra Hamiltonians for the spin model are obtained by using this supply of functions. Okay, so maybe I'll so A and B are just any non-negative integers. So it's infinite set. Yes, it's an infinite set. Of course, you only need finite number of generators, but it's a difficult problem actually to describe how many you need and what are possible relations between them. That's a difficult question, but it's enough to take all right. So that's that's the. And then you take products as well. So it's not just a linear basis, it's a set of generators. Okay, so maybe I'll keep maybe those two on the board and move on to. Okay, so that's the first kind of new result which we need here is that we have more than this statement that we have more than n. We have big algebra of commuting Hamiltonians for the spin model. Okay, and now I'm ready to. Yeah. Okay. Yeah. Thank you. Let's look at a few examples. What you can do. Yes. So. I will be just writing combination of y with lambda dependent coefficients if needed, but the simplest one is just to take when a is in this definition a is 0, y is 1, it's trace of y, just sum of p's. P's are replaced with Dunkl operators, and in this case it's just you get just the conservation of total momentum, right? Nothing. You don't need to take lambda equals 0 limit. It's already, it doesn't depend on lambda. Okay, so that's the first one. It's actually not. It's the same as in the scalar case. Okay, if you take something Yes. So if you take sum of squares, we already know what happens, right? If you take the sum of squares, that was erased. So in that notation, it's trace of y squared. You get this, and then this produces. Then you need to take a limit lambda goes to 0, and then applying this bosonic, this spin version of restriction, you get this the Hamiltonian. And the less trivial example, which I can take, is it's a more complicated combination. I didn't do it by that formula with the matrices, but I know that this function would just lives in this spherical subalgebra. So that's what you get. So this roughly is a quadratic combination like quadratic Hamiltonian, but then you put lambdas as well, and sum is over. Yes, J, I, J, K are all different. And then if you take lambda goes to 0, you get, okay, let's call it HF spin, which will look like, okay, I can write it on the board. So you see what happens. The leading terms here, they have quantum momenta, but then they come with lambda, and lambda goes to 0. So leading terms actually disappear. So yes, like in the previous example, correct, yes. So what this does, it tells you that by having these extra things in front, you can kind of dig deeper into these Dunkl operators and extract something from further kind of below. And so, at least morally, this reminds to me the method for constructing extra Hamiltonians of the classical spin color-germal system. When you look at the Lux matrix and then you expand into spectral parameter and collect the terms of these expansions. So at least morally it looks kind of similar, but it would be nice to make it to clarify these. But yes, and so this one I would like to have on the board to illustrate them. What you get is something which actually was calculated by Inozemtsev as well when he explored this. So what you get is this leading term and then g squared I less j less than k zeta xij plus zeta xjk plus zeta xki eijk minus pkji. Okay. Oh, zeta is standard zeta function, so its derivative is negative p function, right? Weierstrass.
So that's I1, right?
Sorry?
I1 on third order.
Ah, well, it is related to I1. Yes, yes. And equilibrium. Yes. So you need to go to the classical limit and set axis to the equilibrium position. Okay. So this now I can yes formulate the now we can move on to spin chain. Yes, and just yeah, I formulate the result and so application of that to spin chains. Right. So we define two types of conserved charges. I don't want to call them Hamiltonians. There are too many Hamiltonians already, so it's a nightmare actually here having all these together, notation and everything. All right, okay. So the first one, it's if you have those functions which are you're allowed to take that from that rational spherical Schrödinger algebra, then you just do as was indicated already, but by people in the audience, right? So you just what I do? Yes. So you take so the commuting charge associated with this function f is just you take f of lambda y. Okay, you take limit. I need more space, maybe. Maybe I'll just you take f of lambda of y, take the limit of lambda goes to 0, and this spin reduction, you get what I called spin Hamiltonian, and then you take classical limit, h bar goes to 0, and then set pi equal to 0 and xi equal to I over n. So that's equilibrium position, and this is IF. Okay, so that's indeed illustration. Now there are so that's one set of charges. Their commutativity is just on the nose. It's obvious because they commute at the quantum level, so they commute at the classical level. There is actually this this even is not so important for commutativity of this. It doesn't play a role. The fact that the position at equilibrium. But now in addition to that, you have more subtle what I call principal charges. Because they are produced from Y's, lambda play no role, they don't interact. So they form a commutative family for this spin model. They all commute at this for dynamical model before freezing. They commute commutative spin Hamiltonians. They all okay. And yes, so principal charges. So that's more subtle. Okay, so what you do, there will be just n minus 1 of them, and so these ones are obtained as follows. So you take now I take classical but not rational. Classical, I substitute Dunkl operators into elliptic. So these were called HK. Then from that you get this thing, and then what happens? So what happens is can be called as kind of separation of spins. So this expression, before doing anything, it splits. You can split it into a non-spin Hamiltonian, quantum Hamiltonian H, which was called like that. So non-spin plus correction, which I will call AK hat. So this is non-spin quantum Hamiltonian, and this is spin correction. Yes, and no. This is a non-trivial fact, and no, sorry, splitting like that is obvious. You can always just take this and everything else you put in the second summand. Yes. Yeah. The non-trivial claim is that this guy vanishes in the classical limit. So this correction is purely quantum. So okay, so that makes it non-trivial, and so that this fact I needed in my earlier work on this quantum lax pairs for Kaluza homomorphism system. So it plays a role in the constructing. Actually, this guy is responsible for constructing a lax partner for the lax pair somehow.
It's also looks like very easy to see, because you demonstrated this correction. So
yeah, but why it's true in general, it's not obvious.
For high Hamiltonians, there would be even more high powers.
Yeah, but at least the trivial part is to prove that there is at least one H bar, at least in the first power. So, in other words, if you use classical Dunkl operators in this calculation, what you will get will be just scalar quantum Hamiltonians. All group elements just disappear. It's not such a. If you do it just with sum of squares of y's, this wouldn't be true. So certainly you need to, if you substitute this into a rational Hamiltonian in general, this would also not be true. So this substituting into elliptic one, it makes it work. Okay, so this goes back to my paper from 2019, and so that this work is kind of afterthought of that. So now, so the theorem is just that all these commute. No, sorry, I didn't say. Now I need to. Yes, this one I can erase because you already see how it relates to the construction. And so this is the splitting property, and so we define the conserved charge, this principal charge, by taking this ik by, so you take this, you divide by h bar, this guy, well, you turn it into a spin version using again, this restriction with spins, rather than as written over there, it lives in the cross product with the group. I need to turn it into spin operator and then take the limit as h bar goes to 0. So classical limit of that makes sense now because ak vanishes. And then in the classical limit you set again pi to 0 and xi to I over n. Okay. All right. So then the result is so all these. Yes. If you do it, why I say that you need to start from k equals 2, because if you do h1 remember was just the total conservation of total momentum. There was no spin contribution, so this a term, the spin correction will be 0, so you would not get anything out of that. And sorry. So this is a commuting family. Okay, so so the proof again, the proof of commutativity of that, as I said already, it's obvious. So commutativity of this, that's where the argument is essentially the same as in the work of Chalykh, Zhitykhin, and Sechin, where they observed similar phenomenon for the trigonometric Dunkl operators. In that case, you just need you take symmetric combination of Dunkl operators, and you observe this splitting of into non-spin and spin part. The trigonometric Dunkl operators can be seen as a limit of this construction where lambda goes to infinity. So somehow the all depends on lambda disappears, and you get just symmetric combination of trigonometric Dunkl operators. So that's how this interacts with their work. They were motivated by this hybrid notion of hybrid systems, and in fact, by combining what they do, you can, as I mentioned earlier, this AK I earlier in my previous work, this is responsible for being the Lax partner in the Lax pair, and from their work you can see actually the reason the same A appears in this linear Lax equation. So there is a relation to their work. So yes, and I wanted to show a generalization. But I think I'm running out of time, right? So there is a way of, yes. So if you do this for so A3, if you follow this recipe and apply 3, it gives you I3 gives I2 found by Inozemtsev. So my notation is should be maybe J instead of I, but okay, found by. Okay, so so that one, which is on the board, appears as one of the principal Hamiltonians. And so commutativity, for example, of I1 and I2 follows from that result, which is conceptually kind of is very clear. And so proof of this I have no time to explain, but it's very simple. Okay, so just one sentence. If you play this game but don't set lambda equal to 0, you arrive at Hamiltonian, which looks like this. I'll write it like that, something with a hat, with a check. So this you view as, you know, in Inozemtsev Hamiltonian, if you wish, you can ignore this all this spin space U and just view it as an element of the group algebra of symmetric group. So you have commuting elements of the group algebra. So this one is not just in the group algebra because there is lambda dependence. So it lives in the cross product of the group with the which acts on lambdas. So there is interaction here. It's not like matrix valued operator where this doesn't interact with coordinates. It does, and so this one you can prove integrability. At least you can construct conserved charges in a similar fashion, and then if you want to interpret it as kind of some spin chain as we did with Inozemtsev, you need to choose representation for this algebra, and there are some different ways of doing that. So you can produce something which looks like kind of deformation of the Inozemtsev model, and in the limit when you send all lambdas to 0, it goes into Inozemtsev model. So okay, thank you very much.